Welcome to my third lectures on advanced linear algebra. In my last lecture, we discussed about while discussing about the system of linear equations, we introduced a terminology called row reduced form of a matrix. We have seen that for a m cross n matrix A defined over a field capital F, one can have a corresponding row reduced echelon matrix of order m cross n. And we have also seen that the system Ax equal to 0 and system Rx equal to 0, where R is the row reduced matrix of A, have the same solutions. Let me quickly take an examples and say it. So, for this let me consider a matrix A of 4 cross 5 order, which is given like this. Now, this matrix, it is not a row reduced matrix because it does not satisfy the criteria of row reduced matrix. So, first let me have a corresponding row reduced matrix. Now, to have the corresponding row reduced matrix, one has to move these ones. See, from this I have to do the elementary row operations. So, the first row is a non-zero row and the non-zero entry is 1. So, I do not have to do anything for the first row. However, I have to make the fifth column which contain the leading entry of first non-zero row, I have to make all other entries 0. So, for that I have to proceed like this. So, second row I will keep as it is 1, 2, 0, 3, 0, then 1, 2, minus 1, 0. So, I will multiply it minus 1 to the first row and then add it. So, if I do it, I will have 2, 4, 1, 10 and 0. So, for first row, both the criteria of the row reduced form are satisfied. Now, let me go to the second row. Second row again non-zero rows, but the first entry appear on the first column. So, therefore, I have to make all other columns entries, all other entries of the same column, first column as 0 please. So, for this what I will do, I will write down quickly like this, the first row as it is, then second row also I will keep as it is 0. So, I have to make first column third entry, that is 0. So, I will multiply minus 1 to the first row. So, basically I am saying that R3 equal to R3 minus R2. So, if I do it, I will have 0, 0 and that is minus 1 and this will minus 4, 0. And for the similarly for the fourth row, I have to make this is 0. So, 2. So, I have to replace basically R4 is equal to R4 minus 2 times of R2. So, if I do it, then I am getting 0, this is also 0 and 1, 4 and 0. Now, we have a new matrix, but still it is not a row reduced matrix because we see that fifth column which contain the leading entry of the first row, all other entries 0, that is fine. Similarly, for the second row, leading entry appear on first column and all other entries 0. But if I see the third row is also non-zero rows and third row's first non-zero entry is minus 1, it appear in your third column. So, if I do this operation again, elementary row operations. So, keeping first, second as it is. So, 0, 0, 0, 1, 1, 2, 0, 3, 0, and so since I have to make it 1, so I can divide by minus 1, I will have the result. So, 0, 0, 1, 4, 0, and then if I just simply add it to this fourth row, I am getting 0, 0, 0, 0, 0. So, now this is a row reduced matrix, because I see it satisfied both the criteria of the definition of the row reduced form, say R. So, let K1 denote the column number, okay, Ki denote the column number of ith row at which leading entry appears. Okay. This implies K1 is equal to, I can say the first 5, and K2 is equal to 1, and K3 equal to 3. Now, since our objective is to answer the question, that is whether a system of linear equations has solution or not, and if it at all it has solution, how to find the solution of it. So, we are looking for a suitable procedure through which we can answer these questions. So, here I am saying that if I consider system Ax equal to 0 and Rx equal to 0, both the system have same solution space. So, solving Ax equal to 0 is same as solving Rx equal to 0. Now, based on that, now I am getting Rx equal to 0. So, Rx equal to 0 implies I am getting 0, 0, 0, 0, 1, 1, 2, 0, 3, 0, and 0, 0, 1, 4, 0, and then fourth one is 0, 0, 0. So, this is my, then I am saying that x equal to x1, x2, x3, x4 and x5. So, this is equal to 0, 0, 0, 0. So, my system is like this. So, I can write down this system Rx equal to 0 in linear equation form, then I am getting what? This implies x5 equal to 0. Then second equation x1 plus 2x2 plus 3x4 equal to 0, and x3 plus 4x4 equal to 0. So, I am getting 3 equations like this. I can also write down this ones xk1 equal to 0, and I can write down again xk2, because k2 is equal to 1, plus 2x2 plus 3x4 equal to 0, and xk3 plus 4x4 equal to 0. So, this implies that I can write down the the solutions for the xk1, xk2, xk3 as if function of x2 and x4. So, assigning any value to x2 and x4, one can have solution, of the given system. But this is for small matrix, small system is all right. When you are talking about the very big matrix, very big system, and you are assigning to the, you want to take the help of computer, then we have to give a proper algorithms for that. So, let me introduce another terminology called row reduced echelon matrix. Row reduced echelon matrix. What is that? An M cross N matrix R over the set of over the field capital F is said to be a row reduced echelon matrix provided it satisfies following conditions. What are the conditions? The first condition, R is a row reduced matrix means it has to satisfy two criteria of the row reduced matrix. Second, all the non-zero rows of R must be above the 0 rows, above the 0 rows. Third one, let R has small r number of non-zero rows. So, certainly R is less than equal to M. Let the leading entry of row 1, row 2, row R appear in column K1, K2, Kr respectively. Then K1 is less than K2, less than K3, less than Kr. So, an M cross N matrix R is said to be a row reduced echelon matrix provided it satisfied these three conditions please. Basically, I can say your Rij equal to 0 for I greater than R and also equal to 0 for I less than Ki. So, this is first one. Second one, Ri Kj equal to, I can write in a canonical delta form delta Ij, which is equal to 1 for I equal to j 0 otherwise when 1 less than equal to I less than equal to R and 1 less than equal to j less than equal to, and third one K1 less than K2 less than Kr. These three conditions can be written also in the same form please. So, let me take an examples first. As usual, zero matrix will be certainly a row reduced echelon matrix. First is 0 matrix. This is trivial examples, 0 matrix. That is, if A equal to 0 0 0 0, suppose if you consider this one, then certainly A is a row reduced matrix, that is first criteria is satisfied, and also all other criteria here are satisfied. So, this implies A is a row reduced echelon matrix, reduced echelon matrix please. Similarly, I can take, if A equal to, let me take identity matrix, then also it is a row reduced echelon matrix. Now, let me take some non-trivial examples. Let me consider A equal to say 0 0 0 0 1 1 2 0 3 0 0 0 0 0 0. So, 0 0 0 0 0. Okay. So, I have taken again as a 4 cross 5 matrix. Let me check, does it satisfy the definition of my row reduced echelon form? Is it a row reduced matrix? Answer is yes. We see that it satisfied all these criteria, these ones. So, next is, does it satisfy two more criteria? Okay. Here leading entry on the first non-zero appears in K1 equal to fifth column, so K1 equal to 5 and K2 equal to 1. So, this implies K1 less than K2 does not satisfy it, not satisfy. So, therefore, this A cannot be row reduced echelon matrix. But if I exchange first row to second row and second row to first row, then certainly you will get a row reduced echelon matrix space. Now, as in the case of any m cross n matrix over the field capital F is row equivalent to a row reduced matrix, here also any m cross n matrix over the field capital F is row equivalent to a row reduced echelon matrix space. Similar to row reduced matrix, here also we can say every m cross n matrix defined over a field capital F is row equivalent to a row reduced matrix. Theorem we can write like this, that every m cross n matrix A defined over a field F is row equivalent to a m cross to an m cross n row reduced echelon matrix. Proof is similar. Similar to what we did to prove that every m cross n matrix over F is similar to a row reduced matrix. Okay, so, I am leaving this one as a homework. So, you can try this one please. So, let me consider problems and show that one can have corresponding row reduced echelon matrix. So, let me take an examples. Say capital A equal to 2, 4, 1, 10 and 1, 0, 0, 0, 0, 0. So, let me consider this matrix. This is basically 5 cross 5 matrix. Now, let me see how to get the corresponding row reduced echelon matrix please. So, for this again we have to do the elementary row operations. So, if I proceed it, so we have to find corresponding row reduced echelon matrix. So, for this let me do elementary representation is 1. So, first row, since the first non-zero entry in the first non-zero row is 1. So, I will leave first row as it is. So, 1, 2, 0, 3, 0 and then since the first column contained leading entry of the first row. So, I have to make all other entries 0. So, for that I have to make it 0. So, I have to this is basically R 2 minus R 1. So, if I do it 0 0 minus 1 minus 1 sorry minus 1 and minus 4 and 0, then 4 0 and 4th row I have to basically replace 4th row by 4th row minus 2 times of first row. If I do it, then it will be 0 0 and this is 1 and again 10 minus 6 equal to 4 and here I am getting 1 please. So, then it is basically 0 0 0 0 1 please. So, A goes to this matrix please now. Okay. So, by elementary row operation, that is here we have done here R 2 equal to R 2 minus R 1 and R 4 equal to R 4 minus 2 times of R 1. So, I have got this one please. Then I see that it still is not a row reduced even not a row reduced matrix also. So, for that I have to do another step. So, the first row I will leave it as it is because it is not violating the rules for the definition of the row reduced echelon form. So, 1 2 0 3 0 and second row I will divide by minus 1. So, it will be 1 4 0 and then third row I have to add this one also, it will work. So, it will 0 0 0 and similarly fourth row 0 0 0 0 then it is 1, then 0, 0, 0, 0, 1. Still it is not a row reduced echelon form, please. So, one more step is required, I think that is 1, 2, 0, 3, 0 and 0, 0, 1, 4, 0. Since all the non-zero rows must be above the 0 rows, let me extend to the third row. So, it will be 0, 0, 0, 0, 0, 1 and fifth row, if I subtract from that third row, then I will have basically again 0, 0, 0, 0, 0 and 0, 0, 0, 0, 0. So, I will have this is the final form, please. Okay. Now, this matrix is a row reduced, this is a row reduced echelon matrix and the leading entries here appearing in K1, I can say that. So, let me write down R equal to as 1 2 0 3 0, 1 2 0 3 0, then second one is 0 0 1 4 0, 0 0 1 4 0 and third one is 0 0 0 0 1, fourth one is 0 0 0 0 and fifth one also same. Okay. So, this is the matrix. So, leading entries appear in the, so K1 is equal to here 1, K2 equal to here 3 because this is your K2, this is your K1 and K3 is equal to 5. So, we see that R is a row reduced matrix and it satisfied the conditions that all the non-zero rows will be above the 0 rows, that is also true, and then the last one that here K1 is less than K2 less than K3 is also satisfied. So, I have a row reduced echelon form, please. So, previously we have seen that every m cross n matrix defined over a field F is row equivalent to row reduced matrix. Then we have seen the corresponding system of equations, because as we have discussed here also the system Ax equal to 0 and system Rx equal to 0, where R is row reduced echelon form, both have the same solution space, please. So, accordingly, now if I talk in the sense of solution point of view, let me write down again the system Rx equal to 0. The system Rx equal to 0, this gives x1 plus 2x2 plus 3x4 equal to 0, then x3 plus 4x4 equal to 0 and x5 equal to 0. So, I can rewrite this one as xk1 plus 2x2 plus 3x4 equal to 0 and xk2 plus 4x4 equal to 0 and xk3 equal to 0. There are 5 variables x1, x2, x3, x4 and x5. Now, I see that this xk1, xk2, xk3 we can express explicitly as a function of rest of the variables. So, this x1 is a coming as xk1, x3, xk5. So, if I consider these 3 variables in one set and others are basically another set, then I can rename say x2 is equal to say u1 and x4 is equal to say u2. So, then I can write down then the system as xk1 plus sigma something like c1 j uj j equal to 1 to 5 minus 3 equal to 0. This is the first equations, and second equation xk2 plus I can say sigma c 2j j equal to again 2 1 2 5 minus 3, that is 2 uj equal to 0 and xk3 plus sigma c3j and j equal to 1 2 again 2 here uj equal to 0. So, I can write down this system of equation in this form also, and xk1 as a explicitly assigning the value of u1 u2. u1 u2 is nothing, u1 is my rename of the variable x2 and x4 please. Here x2 and x4 are treated as free variable please. So, you assign one value to x2 and x4, you will get one solutions. So, from this I can also clearly say that this system has solution. Not only solutions, it has non-zero solution also. Certainly each equation satisfied 0 0 0 as a one of the solutions. There is in each of them represents is basically plane in 5-dimensional space please. That we used to say basically hyperplane. So, each of them represent a hyperplane in 5-dimensional space and each plane passes through the origin, therefore, they intersect the point 0 0 0 origin place. So, in the origin will be by default a solution. So, 0 0 0 0 will be the by default a solution, but apart from 0 solution one can have non-zero solution, that is called non-trivial solutions. Here for these problems we see by assigning that 5 minus 3 variables and we have the solution please. Okay. So, let me generalize this concept. In general, if A is a m cross n matrix over F is the set of field basically and R is the corresponding row reduced Echelon matrix. Let R has small r number of non-zero rows and let the leading entry in row 1, row 2, row R appear in column K1, K2 and Kr respectively. This implies the system Rx equal to 0 will have basically R equation basically. As in the case of previously I have shown through the examples, even though R is a 5 cross 5 matrix, but it has only 3 non-zero rows. So, we have only 3 equation please. Okay. So, I will have small r number of equations. Let me consider the variables xk1, xk2 and xkr. These are the variables from the set x1, x2, xn. So, I will take out these variables. So, rest will be n minus r variable please. Consider the rest n minus r variables as list n minus variables and rename as u1, u2, un minus r. Then this system Rx equal to 0 can be written as by the system of equations like this. First is xk1 plus sigma your c1j and uj j equal to 1 to n minus r equal to 0. Then similarly sk2 plus sigma c2j uj j equal to again 1 to n minus r equal to 0 and xkr plus sigma crj uj your j equal to 1 to n minus r equal to 0. So, I will have a new system here having r equations, and so I have n minus r free variables assigning to any n minus r variables to any as a constant value, one can have solution please. See this one for homogeneous system. One can also generalize this concept for the non-homogeneous system also. So, in that case I will have, so for that let me consider the non-homogeneous system say Ax equal to your capital Y. Consider in an augmented matrix, A prime, which is m cross n plus 1 order, and the n plus 1 column is right hand side column vector capital Y please. And then one has to do the elementary row operations. So, one will get from this A prime, which is basically it is something A colon Y type, this is this matrix. So, this matrix when you translate through the elementary row operation, then multiplying each time elementary matrices, I will have, suppose through this sequence of process I will have R1Z type. So, I will have this type of matrix please. So, here R is a row reduced echelon matrix please, echelon matrix. So, basically R is obtained as a multiplying a finite number of elementary matrices from the left side to the capital A. So, it is like this. So, R is equal to something like, say we have multiplied, suppose say small k number of elementary matrices. So, E k minus 1, so like this, and E2 and E1 and then A, okay. Or since each of them are invertible, so I can say this is equal to something P into A please. So, row reduced echelon form R is basically obtained multiplying invertible P matrix to the left hand side of the A. Similarly, the Z column is obtained as basically multiplying P to your capital Y. Now, if R has exactly small r number of non-zero rows, then it has m minus r 0 rows. So, in that case I will have xk1 plus sigma c1 j uj j equal to 1 to n minus r equal to say z1 and xkr plus sigma crj j equal to 1 to n minus r uj equal to zr. Then I also have 0 equal to zr plus 1 and 0 equal to it will be zm. The required condition for the existence of the solution of original system Ax equal to y. See, if you look these things in bit geometrically way, so what does it mean that zr plus 1 equal to 0 to zm equal to 0? This will basically introduce a parallel plane if I do not consider zr plus 1 equal to 0. If any of these are non-zero, that will introduce a plane. This will show that in your system Ax equal to y, which basically consists of m plane, that there are some plane which are parallel. See, for examples, if I take say x1 plus 2x2 equal to 1, and if I consider again say x1 plus 2x2 equal to say 4, then if I do the elementary row operations, I am basically writing this is 1 2 1 2 x1 x2 equal to 1 4 through this augmented process 1 2 0 0 1 2 0 0 1, and here I will have basically 3. Okay. So, I will have this type of system please. So, this means that I will have system x1 plus 2x2 equal to 1 and 0 equal to 3, which is meaningless. So, I have to make that zr plus 1 to zm has to be equal to 0. Okay. So, that is the basically the criteria for existence of the solution of the system of equation Ax equal to y. So, let us quickly summarize what we have learned. So, we have seen that concept row reduced matrix helps to find the solution of the system, to talk about the whether system has solution or not, but more proper way one has to introduce the row reduced echelon form of the given matrix please. And through that one can say whether system Ax equal to y has solution or not. If it has solution, then by assigning the free value of the free variables, one can have the different solutions of the system Ax equal to y. Thank you.